Integrals of trig inverse functions. That is, integrals whose answers are trig inverse problems. Suppose you have such a problem. First thing you should do is try not to use trig inverse functions. Now, if you let u equal this, well, what's left over is not a multiple of 18, of x squared. I can get the negative 18, but I don't have x squared. I just have 1 left over. That is, if I had an x in the top, this would be a very, very different integral. I can use trig substitution if I wanted to, but you don't need to. If I let u equal the denominator, so in the bottom I have u to the 1/2, then the numerator would be then du, would be negative 18 dx. Well, I have the x dx. I would just put in a negative 18 and bring out the reciprocal, and then I have a nice simple u to the n integral, u to the negative 1/2 du. This is simple. Add 1 to their power and then divide by that new power. And then substitute back. But we didn't have that x on top. So what you want to do is you want to make a right triangle. Call the angle something, say u, and the square root of the positive part goes on the hypotenuse. The square root of what's after the negative sign goes on one leg, and the whole square root goes on the other leg. And Pythagoras will back this up. Now, you want to find dx. Well, it'd be nice if you knew what x was or what 3x was. So you look at the angle and you say, you know what? If I divide 3x by 1, I'll get close to x. And that involves the sine function. The sine of u is 3x over 1, which is 3x. So then cosine u du is 3 dx. Well, I have the dx. I just need the 3. I just need the 3, so I'll bring out a third. So right now I have 1/3 and cosine u du on the top. Now the bottom, what is this? Well, if I divide this side by 1, I'll just get that, and that's the cosine of u. The cosine of u is identically the square root of 1 minus x squared. Okay, cosine of u. But this is great because this cancels out and you just have 1/3 du. But that's just 1/3 u. Now, from here, you can say that 3x sine inverse of 3x is equal to u. So the final answer is 1/3 sine inverse of 3x plus c. You're allowed to interchange these two as long as you put, if there is no inverse, well then you put an inverse. So there is the answer, 1/3 sine inverse of 3x plus constant. About the integral of dx over 1 plus 4x squared. Once again, if you call 4x squared or 1 plus 4x squared u, well then du will be 8x dx. And although we have the dx, we don't have the 8 dx. So what you should do is think of the bottom as 1 squared plus 2x all squared. And if you want, you can make a u substitution right there. If you let u equal 2x, well then du will be 2 dx. So now I put the 2 in, and now I have the 2 dx, but I have to counter it with a half. So there's a half. This is du. And the bottom is 1 plus u squared. And you do enough for these integrals and you'll realize that that integral is just the arctangent of u. But if you don't know that, since everything is positive, 1 plus u squared square root goes on the hypotenuse. The square root of u squared goes on one leg, the square root of 1 goes on the other leg. And we'll call the angle u. Once again, we'd love to find du. Well, tangent of v is just u over 1, or u. That's perfect to find du, because the differential of u is du. Differential of tangent v is secant squared v dv. Okay, so what we have is the 1/2, the du, well that's secant squared v dv, and 1 plus u squared. Well, if you divide this by 1, you'll just get that, and that's their secant. The secant of u is the square root of 1 plus u squared. But if I square it, if I square the secant u, I just get 1 plus u squared. So the bottom, which is 1 plus u squared, that's secant squared v. That cancels out. You get 1/2 of the integral of dv, which is v, plus a constant. Well, what's v? You could interchange those. U is v. V is the arctan of u. So we have 1/2 the arctan of u plus c, and then one more substitution change. I gave you a problem involving x's. Don't give me back a problem involving u's. And we said u is 2x. So there's your answer. Let us try another one. The integral of arctan of x, or tan inverse of x dx, divided by 1 plus x squared. Now, there's two ways of doing this. You can let u equal the denominator. Sorry. Let u equal arctan x, or tan inverse x. Okay, so we know what that is. That's u. Now my goal is to find out what dx is. So x is equal to the tangent of u. And then dx will be secant squared u du. That is what dx equals. Okay, so what we want to do is we want to build this up. Well, we want to build up 1 plus x squared. So 1 plus x squared, that's 1 plus tangent squared u. But now remember that sine squared u plus cosine squared u is equal to 1. If I divide both sides by cosine squared u, this becomes tangent squared u plus 1, and 1 over cosine u is secant u, but I have 1 over cosine squared. This is just secant squared u. Okay, so octan became u, dx became secant squared u du, and the bottom also became secant squared u. Okay, so that cancels out, and what you're going to get is just the integral of u du, which is u squared over 2. So you're going to get u squared over 2. Well, u is octan of x. So you get the octan of x squared over 2 plus a constant. That is one way of doing this problem. Another way of doing the problem, well, first let's write it down. The tan inverse of x divided by 1 plus x squared dx. So what we can try is the following to make a trig substitution. That means make a triangle. Since the 1 and the x squared both have a plus in front of them, the whole thing under the radical goes on the hypotenuse, and the square root of x squared goes on one leg, the square root of 1 goes on the other leg. And the tangent of u will just be x over 1, or x. Well, that's good because that helps me find dx. Secant squared u du is dx. So I have that. Now, if I interchange those, I get that the octangent of x is u. Ooh, octangent of x. I need that. And 1 plus x squared I can get by squaring both sides and adding 1, or I can say that the secant of u is this over 1. Well, I don't want that, but I want that squared, so I square both sides. Okay, so let's come down here. Octangent of x, that's u. Dx, that's secant squared u du, and the bottom 1 plus x squared, look at that, it's secant squared u. Well, that's going to cancel out, and like before, you get u du, which is u squared over 2 plus c, u squared over 2 plus c, and u is, well, it doesn't say what u is, but it says what the tangent of u is. Interchanging those two, it tells you that u is equal to the tan inverse of x. Okay, u is the tan inverse of x. Both ways, same level of difficulty. I fail, but most importantly, we got the same answer. Remember, they do look the same, but they didn't have to look the same. They can differ by a constant. Now, suppose you have the integral of x dx divided by 1 minus x squared. Square root. Now, I would definitely use u equals 1 minus x squared, because du will be a multiple of that. It'll be negative 2 x dx. Well, I have the x dx. I just need the negative 2. And I have to bring out negative a half. So the top is du. And the bottom is the square root of u. That is u to the half. But we don't know how to integrate u to the half. So we bring it to the numerator, and then we do know how to integrate it. You add 1 to that exponent, it becomes a half, and then you divide by 1 over 2. Dividing by 1 doesn't do anything. The 2's cancel out, so you get negative 1 square root of u. And plus c. And just substitute in where u was. Don't guess. Plus c. Okay, so this one, it looked like a trig interval, but it didn't turn out to be one. This is a similar one. What if you have x dx over 1 plus x squared? Don't jump on doing trig substitutions. If I call this u, well then du will be 2x dx. And this is a very simple integral. It's 1/2. Du is on top, u is on the bottom. Integral of du over u is an integral that you're supposed to know. Ln of u, absolute value of u. Now just substitute back in what u is. 1 plus x squared plus c, and you don't even need the absolute values, because 1 plus x squared is more than 0. X squared can be 0 or bigger. If you add 1 to both sides, x squared plus 1 is bigger than 1. Maybe I should have written it the other way. X squared is either 0 or positive. You add 1, and 1 plus x squared, or x squared plus 1, is bigger than 1. That means it's bigger than 0. It is always positive. If you're 1 or more, you're positive. So you don't need the absolute value bars. Now, in my opinion, an insane way to do this problem would be to use trig substitution. You have 1 plus x squared. They're both positive. So you put the whole sum under a radical on the hypotenuse. X squared, put the x here. And understood 1 squared, put the 1 here. Call the angle u. Well then, the tangent of u is x over 1. Which is good. We like that, because then you can easily get dx. Secant squared u du, that's dx. So we don't have this anymore. Well, I have the dx. That's good. And I even have the x. That x, that's good. I have 2 of the pieces. Now I need 1 plus x squared, which is right there. Well, if I divide this side by 1, I just get this. Well, that's the secant of u. But I don't want the square root of 1 plus x squared. I want it squared. Okay. So this integral becomes x, which is tangent u, okay, tangent u times dx, that is secant squared u du, and then the bottom is 1 plus x squared. Let's see, oh, that's secant squared u. This cancels out. We get the integral of tangent of u du. Well, that's the integral of sine u du over cosine u. If I call that v, well then negative sine u du, that will equal to dv, but I have to put a minus out. So that integral is easy. That's just ln of cosine u plus c. But what is cosine of u? It's negative ln of. Cosine will be this over that. So it's ln of this over that plus c. Now this minus sign says to take the reciprocal of that. It goes up as the power. So we get ln of the square root of 1 plus x squared plus c. And now I need to explain I was going to say that they're different, and I have to explain why where my mistake was. But remember, this half can go up as the exponent. So it's just ln of the square root of 1 plus x squared plus c. Okay, and like I said earlier, square roots can never be negative anyways, but this is at least 1, and the square root of at least 1 is positive. So you don't need their exponents. 1 plus x squared plus c. But we did it 2 different ways, and we got the same exact answer. Square root though. Okay. Let us see the next one that we want to do. A few more. Suppose you were asked to evaluate this integral, where the denominator is x squared minus 2x plus 2. Now the derivative of the denominator is not on top. You don't have x minus 1 on top. You don't have a multiple of x minus 1 on top. Where am I getting x minus 1 from? The derivative of the bottom is this, which is 2 times x minus 1. You need this, because you can always put the 2 in. If you have a 7, you could factor out the 7, put the 2 in that you need, and then divide by the 2 that came out of nowhere. You put this 2 in because you needed it. It wasn't there. So then you have to balance it with dividing by 2. But we don't have any multiple of x minus 1 on top. So you need this thing, basically trig substitution. You need to make the denominator a perfect square. So you do that by separating off the constant. And then what you do is you take half of that number, half of negative 2, and it's important to know what that is. It's negative 1, and to write it square. That means you have to add 1. But if you added 1, to the denominator, you better take it away one somewhere. And I just did. So now we have dx over x followed by half of that number. Half of -2 is right there. And that's what goes next to the x, and it's squared. 2 minus 1 is 1. Now one thing you can do is let u be x minus 1, then du is dx. So the top is just du, and the bottom is u squared plus 1. U squared plus 1. And what you can do is draw your triangle. Everything's positive. What the sign in front of the u squared is positive. The sign in front of the 1 is positive. That means the whole thing goes on the hypotenuse with the square root. The square root of that goes here. The square root of that goes there. I could have switched the order of those two. Let's call the angle V. Well, I would love the tangent of V. It's u over 1, which is u. That means I can find du. Secant squared V dV is du. So I have du. Now I want to know u squared plus 1. Or even the square root. Because once I get the square root, I can square it and I'll just have u squared plus 1. Well, let's see. The secant of V, that is u squared plus 1 square root. But if I square this, I don't need the square root sign. And when I square that, I do need to say that it's squared. So now I have the bottom. So this is du, which is secant squared V dV divided by u squared plus 1, which is secant squared V. This cancels out. I just get the integral of dV, which is V. This here tells me that the arctangent of u is V. Okay, so I get the arctangent of u. And maybe I put the plus c's in now. And the last thing is u was x minus 1. X minus 1 plus c. And there's that answer. What if you have this problem? Suppose you're asked to evaluate the integral of e to the 2x over 1 plus e to the 4x dx. Well, if you call this or 1 plus that u, the problem is du, whether you have the 1 or not, du is going to be e to the 4x times 4 dx. But you don't have e to the 4x. So that gives you a problem. And then you think, well, you know what? The bottom is 1 squared plus e to the 2x squared. And let's see what happens if we let u equal to e to the 2x. Then du would be 2 e to the 2x dx. Well, I have e to the 2x dx on top. I just don't have the 2. So I bring in a 2, I bring out a half. There's the half. This, 2 e to the 2x dx, that's du. And in the bottom I have 1 plus u squared. 1 plus u squared. Okay, let us figure out what that is. It's going to be 1/2 or something. So we draw a triangle. We'll call the angle V. Both of the terms are positive. So I put the square root of it on the numerator. U squared, I put u here. 1 squared, I put 1 there. For the record, if it was 3 plus u squared, this here is u squared, and that there is square root of 3 squared. So I would put square root of 3 here. But it's 1. Well, the tangent of V is so friendly. It's u over 1 or u. I really like that because I need to get du. Secant squared V dv, that's du. Well, 1 plus u squared. Ooh, if I divide those two sides, I get the square root of 1 plus u squared. And that would be secant of V. And if I square it, I get the square of secant V. Okay, so the numerator du, that's secant squared V dv. And the denominator, 1 plus u squared, that's secant squared V. This cancels. You have 1/2 the integral of dv, which is v plus c, and now we substitute back. V was, interchange these, and put inverse. The arctangent of u is v, so it's the arctangent of v plus c. And then lastly, plug in what v is. Okay, hold on a second, please. So V, that V is the arctangent of u. And u was e to the 2x. E to the 2x plus a constant. If you don't believe this is correct, you take the derivative of this. If you want to check if it's right, you take the derivative of that, and you will get something that equals that. How about this problem? The integral of 2x dx all over x squared plus 6x plus 13. Now, if you call that u, if you let u equal x squared plus 6x plus 13, well then du will be 2x plus 6 dx. Well, you have the 2x, you don't have the plus 6. Now if you want to, 2x is equal to 2x plus 6 minus 6 dx all over x squared plus 6x plus 13, and this will give you, let's write two separate integrals. You have this over that minus 6 over that, both dx. Now the thing is, the first integral is pretty easy. You call that u, and then du is right on top, so you're just going to get ln of the bottom. The problem is this integral is not that easy. That integral is not that easy. And what we have to do to that integral, we could have done to the very first integral. That is, this u substitution right here wasn't such a great idea. It'll get you part credit because we found the first answer. I'd give you half credit for that. You broke it up into two integrals and you solved the first one. That sounds like 50% to me. What we want to do here is we want to complete the square in this denominator. You have x squared plus 6x plus 13. Half of 6, that's positive 3, squared is 9. You want to add 9 and you want to take away 9. So what you now have is, and we're going to pull a 2 out in front. So you have x dx on the top. You have this being something squared. What comes next to this x? That number plus 3 squared. 13 minus 9 is 4. Okay. Maybe we let u equal x plus 3, so du equals dx. So you have 2 times, well, the problem with that, and it's not such a big problem, is that that's u squared plus 4. That's the bottom. U squared plus 4. But then the top is, if I take away 3 from both sides, I get u. I get x is u minus 3. Well, this is no bargain. This is no bargain. Okay, so we'll live with the x plus 3. So since both terms are positive, the x plus 3 squared and the 2 squared are both plus, the whole thing goes on the hypotenuse with the square root sign on top of it. One side gets x plus 3, the other side gets 2. And I need x and dx. Well, it turns out that the tangent of v is x plus 3 over 2. I'm going to put the over 2 up there. The differential will be 2 secant squared v dv equals dx. So I have dx. And if I bring 3 to the other side, I have 2 tangent v minus 3 is x. So I have the x. Now I just need the bottom. Well, once again, the secant of v is x plus 3 squared plus 4 square root over 2. I'm going to put the over 2 on the other side. If I square both sides, I get x plus 3 squared plus 4. Okay. So this integral becomes, the 2's in the front, x is this, 2 tangent v minus 3, that's x. dx is this. I'm going to put the 2 in the front, 2 secant squared v dv, and the bottom, well, that's 4 secant v. And I'll put the 4 in the bottom, and in the front, that kills off the 4 already in the front, and I have secant squared v, and this cancels that. Okay. So now, this gives me the integral of 2 tangent v minus 3 dv. And write this as two separate integrals. The integral of 2 tan v dv, pull the 2 in the front, minus the integral of 3 dv, and I pull the integral in front. The integral of tangent v is negative ln of cosine v minus 3v plus c. Let's not lose that minus in front. Okay, so this is equal to negative 2 ln of cosine of v. Well, cosine of v is adjacent over hypotenuse. It is 2 over x plus 3 squared plus 4 minus 3v. Well, we know from that equation that tangent of v is x plus 3 over 2. So I can interchange those two. So the tan inverse of x plus 3 over 2, that's v. So it's minus 3, the tan inverse of x plus 3 over 2. And I'm not sure how I didn't write the 4, but there's the 4 right here. Plus c. Well, there's that integral. So it looks here to me, the fact that I got a subtraction here, it would have been no big deal if I did do the trick that I was saying to do initially. Remember, if that's u, the derivative is 2x plus 6. So we could have written the numerator as 2x plus 6 minus 6 dx all over x squared plus 6x plus 13, this integral. This is equal to the integral of 2x plus 6 over the denominator, which is just ln of the denominator, because if I call that u, well then the whole top is du, minus, I'll pull out the 6, dx over x squared plus 6x plus 13, and then you would complete the square on that one. So here I separated it into two integrals early on, and the way I did it down here, I separated it into two integrals later on. Either way, it did have to be separated. You should have seen that. Okay. Let us do one more for this section. Suppose you have the integral of dx over x minus 1 times the square root of x squared minus 2x. I would complete the square here. Half of that number is negative 1. You square negative 1, you get 1. So we're going to add 1, and we're going to take away 1. So this becomes the integral of dx over x minus 1 square root of, half of that number is negative 1. So it's x minus 1 squared minus 1. Now, if you like to make it cleaner looking, you can let u equal x minus 1, and then du is dx. So the top is just du, that's u, and that's u squared minus 1. Now this is one of the integrals that they ask you to memorize. I forgot it 20 years ago, but I still have it anytime I want it. That's what's important. I want to write this using our triangle. It's positive u squared. So the square root of that goes on the hypotenuse. And it's minus 1 squared. So 1 goes on one leg and the square root goes on the other leg. Now, the secant of v is u over 1, or u. That's what I like, because then secant v tangent v dv is du. And I love having du because I always have du. Okay, and now I have u as well. That's secant v. I just need this u squared minus 1. Now, I can square u and then minus 1, or I can say, hey, the tangent of v is that over 1. The tangent of v is u squared minus 1. So, I have du, which is secant v tangent v dv all over u, which is secant v, it says so right here, and then that square root part, which is tangent v. Look at that. Everything canceled out except the dv. Integral of dv is v. So what is v? Well, secant inverse of u is v. So this is secant inverse of u plus c, which is secant inverse of whatever u is plus c, and u is x minus 1. And there's your answer. Okay, it turns out that the integral of this, people actually remember. Okay, if you're taking the course and you do enough of these problems, you're gonna know, oh, this is secant inverse of u plus c. You're gonna know that. And then you say, oh, I let u be x minus 1, so replace u with x minus 1. Exactly what we got. The way I do it, you don't have to remember it. Okay, it takes a lot longer. I mean, I didn't have to do any of this. I didn't have to do any of this if I remembered that this integral is secant inverse of u. And that I did make the substitution that u was x minus 1. Okay, I didn't need this part, but I did need that substitution. Okay, that is du, dx is du, this is u, this is u squared minus 1 under a radical. Ooh, I remember that. That's arcsecant of u plus c. Just substitute back in what u is. But who wants to remember this? I surely don't. Okay, that completes this section.